Hi, this is Barrett Givens, and in this video, I want to talk about equivalence relations, partitions, how those two concepts are connected, and do a couple of examples. Okay, so the definition of an equivalence relation is that an equivalence relation on a set X, it's a binary relation, squiggle, a binary relation, which satisfies these three properties, which are sometimes even referred to as the axioms of equivalence relations or the properties of equivalence relations. Okay. And you can kind of see what a binary relation means here. It's a way, this sort of squiggle is a way of saying, like, oh, these two things have this relationship with each other. Okay. So, first of all, we have the axiom that says X is equivalent to X, X squiggle X for all X. Secondly, if X is equivalent to Y, then Y is equivalent to X. If X is equivalent to Y, then Y is equivalent to X. And then thirdly, if X is equivalent to Y and Y is equivalent to Z, then X is equivalent to Z. So the squiggle doesn't have to be called is equivalent to. It might be something like is congruent to, or is homeomorphic to, or is isomorphic to, but it somehow is conveying that they're the same in some way, or they're equivalent in some way, hence the name equivalence relation. And so when you just don't know exactly what the relation is, in this case, you might just sort of read the squiggle as is equivalent to. But in different settings, it might be called different ways. All right, and then these things have some names. So the X being equivalent to X, this is called the reflective property. And I always think of it as reflecting like in a mirror. This is saying X is equivalent to itself. So X is like looking at itself in the mirror saying, yep, we're the same. Okay. And then the property that if X is equivalent to Y, then Y is equivalent to X. That's called the symmetric property. It's kind of like commutativity, except commutativity is a way where you take two things and you combine them and you get an output. This is more like expressing that X and Y have this relationship. But if X is kind of the same as Y, then Y is the same as X. That makes sense. And then the last one is called the transitive property. The transitive property. If X is equivalent to Y and Y is equivalent to Z, then X is equivalent to Z. You could think of like congruence in geometry, where you're proving that like angles are congruent or something. That means their measures are equal. And so basically any kind of relationship where you're kind of imagining this relationship is expressing that somehow these are essentially the same thing. All right. So now a related concept is the concept of a partition. A partition on a set X is a collection P of pairwise disjoint sets whose union is X. Pairwise disjoint sets whose union is X. So if I imagine X looking like this, the partition would be a way of carving X up into pieces. P1, P2, P3, P4, P5, P6. So script P is a collection of pieces of X. They're pairwise disjoint. That means no two of them overlap. And their union is X. So that means that everything in X is included somewhere in this carving up. So think of a partition as a way of taking the set and dividing it up into separate pieces with no overlap between them. Okay, so that is a partition. All right, let's see a couple of examples. So let's first talk about the example of the relationship on the reals given by X is equivalent to Y if and only if X equals plus or minus Y. X equals plus or minus Y. So in this relationship on the reals, for example, 1 and minus 1 are equivalent. So 1 and minus 1 are equivalent. 2 and minus 2 are equivalent. So 2 and minus 2 are equivalent. What's equivalent to 0? Just 0. 0 is equivalent to itself, but that's it. Okay. Does this satisfy the conditions of a binary relation? Is it true that X is equal to plus or minus X? Yes, actually X equals plus X, but it's plus or minus, so plus works. Okay. If X and Y are related, if X and Y are equivalent if X is equivalent to Y, does that mean Y is equivalent to X? So if X is equal to plus or minus Y, does that mean Y is equal to plus or minus X? Yes. And then the transitive property. If x is equivalent to if x is equal to plus or minus y, and y is equal to plus or minus z, does that mean x is equal to plus or minus z? I say yes. Okay. So this is an equivalence relation. Okay. Now I claim that from this equivalence relation, I can build a partition. And I will say that that is the partition induced by this relationship, induced by this relationship. So the partition induced by the relationship is the partition that I get by saying, okay, I'm going to partition it into equivalence classes. That is, I'm going to partition it into sets of things that are equivalent to each other. So what would be the sets in the partition? Well, let's start with our favorite number, 0. What's equivalent to 0? Just 0. Okay, so that's that. What about what's equivalent to 1? -1, and that's it. What's equivalent to 2? -2, and that's it. So I'm going to make sets, and each set is going to consist of everything in that set should be equivalent to each other. Those are called equivalence classes. So I claim that the partition here consists of sets of the form x minus x, if x is not 0, and then singleton 0. So this is my partition that comes from this equivalence relation. And the idea is that the partition, the sets in the partition, consists of all the things that are equivalent to each other. All right, so that's one example. Let's do another example. Here I'm going to start with a partition. So I'm going to partition Z into these 3 sets. So let's check that this satisfies the definition of a partition. First of all, are these sets pairwise disjoint? If I take any 2 of these 3 sets and I look at their intersection, is the intersection empty? Okay, so the first set is multiples of 3. The second set I obtained by taking all the multiples of 3 and adding 1 to them. And the third set I obtained by taking all the multiples of 3 and adding 2 to each of them. So are these disjoint? Yes, these are pairwise disjoint. And then secondly, is there union all of your space? Well, my space here is the integers. So when I union up these 3 sets, do I get everything? I think so. You can kind of see it if you were to look at them. I get -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And you can imagine that that keeps going. And so, yes, this is a partition. Okay, so that's an example of a partition. And then I can also ask, what is the equivalence relation induced by this partition? What is the equivalence relation induced by this partition? So what I'll do is I'll say that any 2 points are equivalent if they're in the same set. So what I'll do is I'll define my equivalence relation to say -3 is equivalent to 0, which is equivalent to 3, which is equivalent to 6, which is equivalent to 9, and so on. And then -2 is equivalent to 1, which is equivalent to 4, which is equivalent to 7, and so on. And then -1 is equivalent to 2, which is equivalent to 5, which is equivalent to 8, and so on. And so basically, all of these points and then all of these points are all equivalent to each other. And then the same thing with the last one, okay? So in each set, we just say, well, all of those points are considered now the same, okay? Let's check that that would satisfy the definition of an equivalence relation. So if I were to take this definition and say, okay, I'm going to call these points equivalent if they happen to be in the same part of the partition, would every number x be equivalent to itself? Yeah, if I take some random number, like let's say I take 7, well, 7 is in this set and 7 is also in this set. So 7 is equivalent to itself because it's in its own set, okay? If x is equivalent to y, does that mean y is equivalent to x? Well, if I say, for example, that 5 is equivalent to 8 because they're both in the same set, well, then 8 and 5 are also both in the same set, so 8 is equivalent to 5. And then would it satisfy the transitive property? If 0 is equivalent to 3 and 3 is equivalent to 6, does that mean 0 is equivalent to 6? Yeah, if you take two that are from a particular set and then another two with the one in, sorry, if you take one element from a set and it's equivalent to another element from the set, and then that other element from the set is equivalent to a third element from the set, all three elements are in the same set, so all three of them are equivalent to each other. All right. So finally, if you don't know any number theory, don't worry about it. But this equivalence relation is essentially saying that x is equivalent to y if and only if x is congruent to y mod 3. If you don't know what that means, don't worry about it. Okay, it's just for people who've taken some number theory or maybe abstract algebra already. All right. So we've seen two examples now. We saw an example where I gave you an equivalence relation and then we defined a partition. And then there's an example where I gave you a partition and then we defined an equivalence relation. And it turns out that you can always do this, and you can kind of see how just based on the examples, I think. So this is a really important fact about equivalence relations, partitions, and surjective functions. So there's a relationship where every equivalence relation induces a partition, every partition induces an equivalence relation, and then an equivalence relation and a partition corresponds to a surjective function as well. So let's just summarize that kind of what we would do. So let's say I have these sort of like three universes of equivalence relations, partitions, and surjective functions from x to x star. So if I have an equivalence relation, I can define a partition. Let each set in the partition be a collection of all points that are equivalent to each other. So we call those equivalence classes, but you don't need to know that terminology, but that's what we would call it, an equivalence class. So you basically clump the points by the ones that are equivalent to each other, and then you make those clumps your partition. If you have a partition, then you say that x is equivalent to y if x and y are in the same set in the partition. Okay. And now how does that connect with the previous concept that we were learning about, which has to do with surjective functions from a space X to a space X star? Well, if I have a partition, I can think of, let X star be the sets in the partition. And I can define rho of X to be the partition set that X is in. And if I want to go the other way, I can let the sets of the partition be defined by when rho of X is equal to rho of Y. So if, you know what, I'm gonna back that up because that was a little confusing way to say it. That was really more what I wanted to say about the equivalence relation. So let's do that. We'll say X is congruent to Y, or X is equivalent to Y, if rho of X equals rho of Y. Okay. And you can check and think about whether or not that would be a equivalence relation. It would. Okay, so I'm not proving any of these facts, but I'm kind of saying how they would be connected. So the two examples that we did previously are good examples of how to think about these ideas of if you have an equivalence relation, you can define a partition, and if you have a partition, you can define an equivalence relation. And then if you have a partition, you can define a surjective function by letting X star, the elements of X star, will be the sets in your partition. And then we'll let rho of X take X to whichever set it is part of in its partition. And then if you have a surjective function, you can define an equivalence relation by saying, well, x is equivalent to y if rho takes x and y to the same thing. And then finally, if I have an equivalence relation, like let's say I want to go, I'm going to sort of cheat a little bit. Let's say I want to go from an equivalence relation back to a surjective function. Well, I can just kind of take the long way. I can turn my equivalence relation into a partition and then turn my partition into a surjective function. And similarly, if I want to take a surjective function and get a partition out of it, I can go the long way around. I can first make an equivalence relation and then get a surjective function. So you can see that the three concepts of equivalence relation, partition, and surjective function can be considered to be almost the same concept, just presented in three different ways. And in the topology class, we are going to use all three ways of thinking about these things. The definition of a quotient topology uses this idea of surjective functions. But oftentimes when we're informally talking about quotient topologies, we talk about gluing or identifying. So gluing is like an equivalence relation. So when we're talking about gluing or identifying, we're talking about equivalence relations. And then when we talk about the partitions, we're often talking about, with a partition, we're thinking of kind of like, what is the output space? What is the identification space? Like we're kind of taking all of these things in our original X and then squishing them down to some point or something like that. All right, we'll do more examples in later videos, which will hopefully make this more clear. Thank you for listening.